Hey everyone. Well, it's been fun studying series and sequences and so on, but it's time to start a new chapter. So we're going to move on, and actually we're going to move back in the book, so we're going back to chapter 10 now. And we're going to talk about curves. And so let's start it like this. So certain curves arise as the graph of a function. So most of what we've been studying in calculus, when we look at various curves, right, they're the graphs of functions. Let's say y equals f of x. And so, our typical picture, right, looks like this. So any point on the graph, right, if that's x, right, then each point on the curve is of the form x comma f of x, right? That's what we do. That's what we do in calculus a lot of the time. But not all curves don't arrive this way. In fact, but most curves do not arise in this way, right? In fact, and I think you probably learned this back in a pre-calculus class, right? As soon as a function fails the vertical line test, right, then it's not the graph of a function, right? And so here's a curve, right? Fails the vertical line test, right? So, let's say this one here is not the graph of a function. And the reason it fails vertical line test. Okay, so lots and lots of graphs or curves out there, right, are not the graphs of functions. And so we would like to be able to study do calculus with curves like this, but if they're not the graph of a function, we don't have the technology at this point to actually study them. So what we need is the next best thing, which is a way to understand curves that don't arise in this way, right? And so that's where we're headed now. So given a curve, say capital C, in the plane, if there are two functions, and let's call them f and g. So let's say f of x. No, actually, sorry. I need to say f of t. I need to use a different variable now. F of t and g of t, such that each point x comma y on C is of the form, or satisfies, let's say satisfies, x equals f of t and y equals g of t. Then these equations here have a special name, right? These are called parametric equations, and the curve C is called a parametric curve. Right? So satisfies this. Then the equations above are parametric equations for capital C, and C is a parametric curve. The variable t is sometimes called the parameters, right? So t is the parameter. So let's come back to this picture now, right? This is not the graph of a function, but the idea would be if each point on the curve can now be described as f of t comma g of t, right? Then what we have is a parametric curve. There are times when our curves have a starting point and a stopping point. And you can think of this as, in fact, there's a reason we choose t. You want to think of this as the motion of some particle in time, or the path of some object in time. And so perhaps here's our starting point, and we travel along the curve, and eventually we get to our ending point right here. So if, all right, so in the case that t is restricted to some interval, so let's say that we need, or that we require t to be between a and b, then there's a starting point, that would be a comma f of a, and this is called the initial point. And the final point, so we'll say and b comma f of b is the terminal point. So in our picture, this would be a comma f of a, and that point right there, sorry, it's a little bit crowded, but that point right there would be b comma f of b. And we really do want to view this so, so we can imagine, or we can view a parametrized or a parametric curve as the path of, I don't know, you can either say particle or an object. I'll say path of an object in space, where f of t comma g of t is the position of the particle. Let me write it below just so we have this picture in mind. So that where this is the position of the particle or the object at time t. Right, so as time elapses, right, this object travels along there, and at each time t, right, f of t comma g of t tells us where we are on the curve. So let's just look at an example here. Here's my equations: x equals t and y equals t squared. And here, we're going to require that t stays between -1 and +2. Now, to get a feel for how this curve behaves, what I want to do is just plot some points. And let me make a little table next to here to see what we're doing, or how what's going on here. So I'm going to label this. I'm going to have 3 columns here. I'm going to label them t, x, and y. And then we just plug in. So I'm going to plug in -1, 0, 1, and 2. So when I plug -1 in, here's what we get. X will be -1, and y will be 1. When t equals 0, both x and y are 0. When t equals 1, both x and y are 1. When t equals 2, x equals 2, y equals 4. So let's plot those points. So first I'm going to have -1, comma 1. Right? That's our initial point in this case. Then I get 0, 0. Then I get 1, 1. And then I get 1, 2, 3, 4 is right about there. All right, so there's our final point. So that's 2, comma 4. And then if you connect the dots, imagining what this is going to look like, right, what we get is part of a parabola. And so you can imagine this as the path of a particle, right? Each of those points on there is the position at time t. Now, this does give us a rough feel for how this curve behaves, but this is not the way to really get the shape of a curve. Right? So there's a better way to do this. Plotting points. You have a couple of homework problems that ask you to plot points, but that's really not the best way to find the shape. So a better way, it's called eliminating the parameter. And it's not always possible to eliminate the parameter, but if you can, it gives you a much better feel for what this curve looks like. So what we get here, if I say, oh, notice that x equals t, I can substitute that in there. And so by substituting into, let me just kind of draw this out. So if I substitute right there, what we get is the equation y equals x squared. That's the familiar parabola shape. And because we required t to be between -1 and 2, it does not cover the entire parabola. It just covers this little portion of the parabola. So let's do another example where instead of plotting points, what I want to do is go straight to eliminating the parameter. So here's my parametric equations. It's going to be x equals e to the t, and y equals t plus 1. And once again, I want to restrict my t values between -1 and +3. So 1 less than or equal to, -1 less than or equal to t less than or equal to 3. Okay, so what I need, when I eliminate the parameter, what I need is a single equation that has no t involved. That's what I mean. Eliminate the parameter, get rid of the t value. And so in this case, there's a couple of different ways to do it, but what I want to do is I'm going to solve for t in the y equation and then substitute it. So what we get is that t equals y minus 1. And then I'm going to substitute that right there. And so what we get is, if I substitute x equals e to the y minus 1. And so that's an exponential graph, although it's got independent variable y and dependent variable x. And so the graph is going to be a portion of the exponential curve. And so let's figure out where it occupies and then get rid of the rest of it. So let's see, when t equals -1, x is 1 over e and y is 0. Right, so it starts right there at the point 1 over e, comma, 0. And then when t is up to 3, we're going to have x is going to be e cubed and y is going to be 4. So somewhere out here, let's say 4 is right there, that's our terminal point. And so this will be e cubed, comma 4. So the portion of the graph that we want is actually the shaded part right here, and it's got direction going like that. And so then we can erase the rest of it by eliminating the parameter and then taking into account what our t values were. That gives us a full picture of what the graph looks like. Okay, let's do another example. So here I've got x equals square root of t and y equals t plus 1. Okay, and in this case I'm not going to put any restrictions on the t value. And let's see if we can eliminate the parameter. Well, what I could do, this tells me that t equals x squared. And so if I substitute into there, what we get is y equals x squared plus 1. That's a familiar parabola. Looks like that. All right, that's at height 1. Now we have to be a little bit careful here. eliminating the parameter can sometimes destroy some information about the curve. And so what I want to ask you, think about this for a minute. In fact, if you can, I'm going to ask the question, put it on pause and think about what the right answer is. So my question is, why does our answer, not our actual curve, not occupy the entire graph? All right, so think about that for a minute. The answer, notice from this equation right here, right, t has to be greater than or equal to 0. And that tells you then that the x-coordinate, right, the square root is always greater than or equal to 0. So the x-coordinate has to be greater than or equal to 0, which means that we only get the right-hand portion. And so the curve goes like this. And that part, you can either erase it or scratch it out or whatever, right? But what you want to notice, t has to be greater than or equal to 0. And if we think of t elapsing, what we get is a curve that goes in that direction following just the right-hand half of our parabola. Now, there's certain important curves that are going to show up both in this class and in future classes. And so you want to be able to parameterize certain curves, right, that'll sort of show up on a regular basis. So the first one, right, we've said that not all curves arise as the graphs of functions, but some do. And if you happen to have a function of the form y equals f of x, there's an easy parameterization for that, right? So in fact, let me say this in a complete sentence. So the curve C given by y equals f of x has parametric equations x equals t and y equals f of t. So anytime if you have the graph of a function, right, we know that each point on there is of the form, right, this is y equals f of x. And so by letting x equals t and y equals f of t, then we can say that this point is t comma f of t. Right? So that immediately gives us a parameterization of any graph, or let's say the graph of any function. The second common one that's going to show up is ellipses. So let's say that we have the ellipse, and there's the standard equation, x squared over a squared plus y squared, or yeah, y squared over b squared equals 1. Now, letting x equal a cosine t and y equal b sine t. Notice that by substitution, right, if you divide, so let's actually do the math here. So if you divide, you get x over a equals cosine t, you get y over b equals sine t. Square both. You get x squared over a squared equals cosine squared. And you get y squared over b squared equals sine squared t. Now, if you add these two together, what do you get? Well, we know that cosine squared plus sine squared equals 1. So what we get is 1, which equals cosine squared t plus sine squared t, which is x squared over a squared plus y squared over b squared. So what that tells us then is that the ellipse x squared over a squared plus y squared over b squared is parameterized with these two equations right here. So let's write it down again. X equals a cosine t, y equals b sine t, right? Gives us a point like that. So that's the point a cosine t b sine t. And so this parameterization right there gives us a parameterization going in the counterclockwise direction. And I shouldn't have boxed this out yet, because if you want one revolution about that, then you would parameterize it like that. All right, so this will take us one time counterclockwise around the ellipse. There is a special case when a equals b. What do you get? Well, then you get a circle of radius a. So remember, an ellipse, or a circle is a special kind of ellipse. It's where a equals b. All right, so you can parameterize circles using this. Okay, so there's two of our important parameterizations. The next one is lines. So say it like this: the line of slope m through the point a comma b has equation y minus b equals m times x minus a, which I want to simplify that or multiply this out. So this is going to be y equals mx plus b minus ma. So all I did was solve for y here. Now, what just happened here? Oh, right. So one way, this is the graph of a function. So one way to parameterize it, so one way, and I should point out, there are always multiple parameterizations of the same curve. So when we're going through these, this is just giving us one possibility for a parameterization. So one way to do this is to let x equals t, right? This is the graph of a function, and y equals mx plus, mt plus b minus ma. But that's not a very convenient one. So alternatively, what I want to do is make a substitution here, and so I'm going to let I'm going to set in this equation right here, I'm going to set t equal to x minus a. So set t equal to x minus a, in which case x equals t plus a. And, not say and, y equals, so I'm going to substitute right here, t plus a, so that will be m times t plus a minus b, plus b minus ma, which equals mt plus b. So a cleaner way to parameterize is to have x equal to t plus a and y equal to mt plus b. One more important one. So this would be number 4, and that's line segments. Especially in Math 241, so if you're going on to Calc 4, parameterizing line segments becomes an important thing in certain settings. So here's one way to parameterize a line segment. So let's say that I have a couple of points here. And I want to parameterize the line segment, and I get a sense of direction here also. So this is going to be the point, I'm going to call it AB. So let's call the starting point A comma B, and the ending point C comma D. Then here is a standard parameterization. X equals 1 minus t times A plus t times C. and y equals 1 minus t times b plus t times d. On, right, where we require t to stay between 0 and 1, right? So this is maybe, I could say maybe it's the most important one. It's the one that probably shows up the most in calculus, with ellipses being a close second. And I want to end with one more famous example. So you don't have to, this is not a parameterization that you're going to need to memorize. I'll always give it to you if we need it. But it does show up. It's sort of an important example. And this gets used in math and especially gets used in physics. So there are important physics reasons for understanding this curve. So here's the idea. What I want to do is take a wheel. Imagine this is a wheel right here. And I'm going to pick a point on that wheel, call it little p. Now what I want to do is roll that wheel to the right. All right? So let's just say roll. And what I want to do is study what's going to happen to that point P as the wheel rolls along. Well, okay, so as it starts to roll, right, the point P starts to go up, 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 up. Eventually, right, it's going to make it to the top. Then as you keep going, it's going to come down. And then once it's done exactly one revolution, it'll be back down to the bottom. And so what you get is a curve that looks like that. And you know, it's going to keep repeating itself like that, right? This is called a cycloid. So the path of P is a cycloid, right? So we'll get a bunch of examples where we need to understand or make use of the cycloid. So here's the parameterization. I'm just going to write it down, and we'll come back and we'll see this a bunch of times. And notice I always kind of forget it, so I'm not going to expect you to memorize it. I always look it up myself. So if the circle has a radius r, then here's the parameterization. X equals r times t minus sine t, and y equals r times 1 minus cosine t. All right, so that is the parameterization of the cycloid. And I think that's a good place to stop for today, so we will see you next time, okay?